Thursday. There should be some around on the desks. How was our long weekend?
Terrible.
Oh no, that wasn't the answer.
He was sick, being deathly sick all weekend. It wasn't deathly sick. It wasn't deathly sick. It wasn't deathly sick. I could have died.
All right, let's open up to page 313. On Thursday, okay, way back when, we were talking about some connections between the equation of an exponential function and its graph. Okay, we're looking at what can the leading coefficient possibly be, what could the base possibly be, where's the horizontal asymptote located. Okay, we were just picking apart little characteristics, trying to get familiar with what certain numbers could be. Today, we're actually going to find the value of those numbers. Okay, do we realize how what we've been doing so far has been kind of vague and generic? We've been saying how A is either positive or negative, or B is either greater than 1 or between 0 and 1. You realize how those are descriptions? Those aren't actual values. Okay, today we're actually going to find the values of those numbers, okay, depending on the graph that we possibly have. So, on page 313, we have this equation at the top, which they're telling us is the general setup that would produce this graph that they also give us. So we're going to have to try to pick apart different things that the graph is telling us and try to translate those characteristics to the equation. Okay, we are actually going to figure out the value for A, B, and C. Okay, we're not going to describe them. Maybe we can to help us check our work, but we're physically going to find the values today. So the first example is kind of going to be a guide as to how we might want to approach finding these different numbers, but we're eventually going to get to the point where I just want you to find them. Okay, I'm not going to guide you. Okay, this is what kind of the section is for, getting a feel for how this might work, but eventually you're kind of going to be on your own. So let's see. The first one says, what is the value of C in the equation? If you take a look at the top, notice how C represents that constant term. So is there something that the graph is kind of hinting us towards that might represent that C value? You have an idea, Caitlin? How'd you get it? Okay, so when we did polynomials, the constant term on the end was the y-intercept. Okay. It's the horizontal asymptote. Okay, so notice how the type of function we have is special, and that's what's telling us something about the equation. So we have to be careful not to get them confused. I know we've dealt with a lot with functions and graphs this year, but they each have their separate special characteristics. So C is -3 because this is the horizontal asymptote. All right, so what I suggest doing is the moment you find the value of some number in the equation, immediately rewrite it. That way you don't forget what that number is, okay? Because from now, the rest of this question is going to use -3 in that C spot. So f of x equals a times b to the x plus 1, and then we'll write -3 on the end. All right, so looking at number 2, it says then find, or then use, I guess find shouldn't be there, then use this information to find the value of A. How might we use f of -1 equals -2? Can we think about what that mathematical notation is telling us? What it represents? Go, Blair? It's an x and y value. Okay, it's an ordered pair. Notice how based off the graph, -1, -2 is a physical point that you have. All right, so if we plug in -1 for x, we should get -2 for y, aka f of x. All right, so let's simplify it. Maybe something's going to happen. they're telling us, they're kind of cluing us into that we should be able to solve for a. So let's maybe try that. -1 plus 1 in the power spot is going to become 0. Where do you want to go from there? What do you think, Lainey? Bless you. This is a property that we talked about previously, okay, at the beginning of this unit, and anything to the 0 power is 1. So this is really a times 1, which is just a. So solving for a, we can add 3 over and get 1. Alright, so notice how I figured out another value. I'm going to rewrite the function with that value in it. So we know what C is, we know what A is. Looks like lastly we got to figure out B. Before we get there though, can we perhaps think about why this point, -1, -2, was used to solve for A? Like, why did they want us to use this point and not any other point? Yeah? Notice how it's strategic, okay? That particular point created a power that was 0 in the end. And if you can get the power to be 0, notice how the base will essentially go away because of that property that turns it into the number 1. So we can strategically look at a graph and pick the special point that would make the power become 0. Okay, it's not any point that we're using here. We have to use kind of a special point and be aware of how to find that, okay, or which one to use. Okay, so we have to be a little strategic to figure out that A value. Okay. Now let's take a look at C. Use another point. Okay, they don't really specify, so this one's up to us. Use another point to determine the value of B in this case. So looking at the graph, can we find a nice coordinate that we can use? You can really use anything. 1, 1, okay. You could have also used 2, 5, okay, but you just have to pick another point. I don't care which one. So maybe we'll use 1, 1. So this is telling us if we were to put 1 in for X, we should get out 1 for Y. Alright, so 1 equals, this would be B squared minus 3. Solving for B, we can add the 3 over to get 4, and then square root both sides. We'll get plus or minus 2. So technically the algebra is leading us to 2 possibilities for the base, but we know the base can only be 1 number. Can we think about which one would make sense? Yeah? Okay, so the positive value. If we think about kind of the descriptions that we've said the B value could be, we've said it could be bigger than 1 or between 0 and 1. Okay, notice how we never included a negative base. So if you do come across that option where you have possibilities, make sure you choose the one that fits either of those descriptions. Okay, bigger than 1 or between 0 and 1. So now that we have all the missing values, the A, B, and the C, we'll write our final equation. F of x equals 1 times 2 to the x plus 1 power minus 3. Can we perhaps use some of those characteristics that we've been discussing so far with exponential functions to see if these numbers make sense based off the graph? Can we kind of check our work maybe? We know the -3 is good because that's the horizontal asymptote, but why does 1 make sense for A? Why does 2 make sense for B? do you think, Noah?
I know there shouldn't be any flips.
There's no flips. Okay, so there's no negative in the power spot on the x, so we're not flipping it left and right. And notice how this graph is not underneath the horizontal asymptote, so we did not flip it upside down. So if there are no flips, then this graph represents one of those basic beginning ones that we've discussed or we've talked about. And if this is exponential or increasing growth, our base should be bigger than 1. So 2 is bigger than 1, it makes sense. Okay, maybe we got 5 here by accident or mistake. That one would still make sense, okay, because it's bigger than 1, but we might have to go back to the drawing board to maybe check that. So we might not be able to check the numbered value, but there is some characteristic that we can use to help us check our work. Since also we did not flip it upside down, that means our leading coefficient should be positive. And notice how our A value is positive. So we might not be able to check the actual value. We're going to have to trust the math with that. But there are some ways we can check our work to see if it makes sense in some capacity. All right, let's go ahead and try another one. This one's not going to be as guided. It's going to be up to us to try to figure these different values that are missing. So they give us the equation in the directions and the provided graph. We got to find A, B, and C. Where do we want to start? Go, Caitlin? C is what? 4? I like it. All right, so g of x equals a times b to the x plus 4. One letter down, 2 more to go. How do you want to approach finding either A or B? What do you think, Noah?
You can plug in the point 0, 2 because you want to get the x minus 0.
Okay, so again, if we strategically pick a point that's going to make our power be 0, that's going to eliminate the base because it's essentially going to become a 1, and we'll be able to solve for A. So looking at our equation, notice how the power spot is just a single x, so that would require us to simply plug in the number 0. So based off the graph, the x value of 0 is associated with a y value of 2. So we have to use this point to help us. Okay, you have no choice with that. So if we, let's see, if we rewrite the equation, we'll get out 2 for y, our x value is 0, and we have the plus 4 on the end. So b to the 0, we said was 1, essentially goes away because it's multiplied by a. Subtract the 4 over, we'll get negative 2. Alright, so we found C, we found A, lastly is B. Actually, this might be a little easy, good for us. First we start with A or C, then we found A, and lastly we found B. Cab, if it helps you with the order. Okay. How do we want to figure out B? Good, Caitlin? Okay, so which numbers do you want to plug in? Negative 4. Okay, so maybe you want to pick this point. You could pick any other easy point on the curve, completely up to you, but you got to pick a point nonetheless. So Caitlin picked negative 2, negative 4. All right, so negative 4 is a y value, and we're going to plug in negative 2 for the x value. All right, solving for B. If we subtract the 4 over, we'll get negative 8. If we divide negative 2 over, we'll get 4. We're getting there. We got a little bit more to do. What do we want to try next? Bless you. Caitlin, I'm happy you picked this point. It's not necessarily the easiest one to pick, but it's going to be a good learning experience here. Our power's negative. Can we use a property to make it positive? Help us out a little bit. How can we make a negative power positive? Go, Blair? We got to flip it, okay? So this would become 1 over b squared. So you're taking a negative power and essentially turning it into a fraction. I know we don't like either of those, negative numbers or fractions, but that's how the cookie crumbles here. Can we keep going? We want to get b all by itself. How can we solve for a variable in the denominator? Yeah? Okay. If you multiply by the reciprocal of this, that would be b squared. So if you multiply this side by b squared, you'll get 4b squared. And if you get this, multiply this side by b squared, you'll get 1. Okay? In layman's terms, you can take the denominator and multiply it to the other side. Okay, and you'll get the same thing. Is that a little bit easier for us to see where we can go from there? Divide the 4. Square root both sides. So plus or minus, let's see, if we square root a fraction, you can square root the top and the bottom individually. So the square root of 1 is 1, and the square root of 4 is 2. We technically have 2 bases here. Which one should we pick? B is, I thought I heard a whisper. Okay, 1/2. So if we write our final equation, g of x equals -2 times 1/2 to the x power plus 4. All right, can we think about perhaps, we already know the C value is correct based off the graph, that's the horizontal asymptote. Can we maybe reason through why our A value and B value were correct, if they make sense? You gonna keep going, Blair? Yeah. Okay, so when you say the graph is negative, what do you mean by that? It's flipped upside down. Okay, it's underneath that horizontal asymptote. So the A value makes sense because graph is below horizontal asymptote. What about the B value? Why does it make sense that we have a base between 0 and 1? What do you know?
Because if you flip it to what the original graph would have looked like, it would have been the
Decreasing decay. Okay, so if we look at the flips, okay, think about the changes that were done. We do not have a negative in the power, so we are not flipping it left and right. But we did identify a negative leading coefficient. Okay, that's the x-axis upside down flip. So if we were to flip this graph over the horizontal asymptote like it was previously, it would probably look something like that. And that decreasing decay original graph signifies a base between 0 and 1, which is what we got algebraically. So we'll say this B value makes sense because we only have an x-axis flip. Okay. If we think about the terminology, we previously said that if we have one flip, I don't care which one it is, if we have one flip, it changes the increasing or decreasing description. So if this graph that we are provided is increasing, that means the original graph was decreasing. If we have a y-axis flip, that changes the growth or decay nature. And we do not have that because the power is not negative. So if this graph we are provided is decay, then the original graph should be decay as well. Okay, which is going to produce that decreasing decay original that we started with. So you can think about the flips, you can go through the characteristics, okay, those classifications, whatever helps you get to that beginning graph description, that's going to help us determine if our result makes sense or not. Okay, so what we're doing today is practice finding these particular values for the A, the B, and the C based off of a graph that we're provided with. Okay, sometimes though we might not have a graph, maybe we just have specific information because we essentially don't need the whole graph, we just need key points or information from the graph. So as long as we have that, we should be able to find the equation. Let's try the one on the next page. Okay, they give us the setup of the equation and they also give us some pieces of information. These are essentially representing points like we've seen previously. So can we think about which point we should use first to help us either solve for A or B in this example? Maybe you want to try both. Okay, if I use the first point, my equation will look something like that. If I use the other point, my equation will look something like that. So if you're not sure where to start, maybe just start with both. Can we proceed further with one of those, both of those, perhaps? What do you think, Caitlin? Is 1. Okay, so if this changes to 1, we're just going to be left with A. So it looks like our A value is 3. So let's maybe perhaps take that A value of 3 and plug it into the other A value from the point we didn't necessarily use just yet. It's kind of like a system of equations. So 15 equals 3 times b to the first. We can divide the 3 over to get 5, and b to the first is just b. So there's our b value. That one was pretty simple. So our equation is 3 times 5 to the x. All right, let's try the next one. Kind of similar setup. This time we have that c in there. If we think about cab, perhaps, can we figure out our c value first? If you read the other information that's provided. What do you think, Olivia? Y, that's good. It's approaching it. Okay, take a look at this last piece. As the x's get very, very large, meaning as you go to the right side of a graph, notice how the y values are getting closer and closer to 3, meaning they're leveling off, some type of horizontal asymptote. So this is kind of a right end behavior that we can use to help us figure out perhaps a horizontal asymptote in this case. So there's our C value. All right, next we want to try to solve for A, and that's going to involve strategically perhaps using a point that's going to make our power be 0. Olivia, did you have another example? Or another case I saw your hand go up? No? Okay. Is there another piece of information that we could possibly use to help us figure out A? Do I know a point that can make my power be 0? What do you think, Caitlin? 0 for x, 2 for y. Good. All right, so b to the 0 is going to become 1. We're just going to be left with a. And subtracting the 3, we'll get negative 1. All right, let's try our last point to help us figure out b. So my x value is negative 4, and my y value is negative 2. All right, so solving for b, let's go ahead and subtract the 3. We can divide the negative 1. Okay, and this is why I was thankful for Caitlin that chose that negative point previously, because notice how we have something similar showing up here. All right, we have a negative power, so we can flip it to a fraction, and the power will become positive. How can we solve for a variable in the denominator? My husband's a chemistry teacher, and he says this is something that not necessarily drives him crazy, but he sees it a lot with his students, that they can't solve for a variable in the denominator. Anybody in chemistry have taken it? What's the equation? Is it like P over V equals P over V or something like that? No, I haven't done that yet? Okay. Well, there's some equation that relates pressure and volume. I think it's this. Sometimes you have to solve for something in the denominator. What was it? I thought something like that. Sometimes, yeah, depending on what information you know, you have to solve for something in the denominator, and some of his kids can't do it. How can we solve? Yeah. Multiply the denominator to the other side. So 5b to the 4th would equal 1. Essentially, okay, in that P over V example, if you have two fractions equal to each other, you can cross multiply. And essentially 5 is 5 over 1. So if you cross multiply with those two fractions, you're going to get the same thing anyway. It just depends on how you want to approach it. All right, so let's see. Solving for b, we can divide the 5. How are we going to get rid of a power of 4? b equals, yeah? The 4th root. There we go. I know it looks weird, but this is still a base value nonetheless. Now, I want to show you, yeah?
Could you just factor out a negative 1 from the exponent on both sides and then put like 5 over 1 and then just b equal 4?
You mean at this stage?
Yeah.
Factor out a negative 1 on this side?
From both the exponents. So like 5 to negative 1 and then b to the 4.
Yeah, that would do the same thing.
That's the last one.
Yep. So if you change this power to positive, you have to change this power to negative. If you switch one, you have to switch both.
Yeah.
Okay? Yep. Because that would lead you 5 to the negative 1st is 1 over 5, and this would be b to the 4th. So that would lead you there. Okay? There's a lot of manipulations that you can do. All right, on your calculator, I want to show you how to get this. There is a root button on your calculator that you can choose any root. We're already familiar with the square root being by the x squared. If you hit the math button, however, notice how number 4 has the little 3 there. That's for a cube root. Do you guys notice 5 though? How it has little x there? If you select option 5, you can move the cursor to where it says that answer ANS value, and if you hit clear, you can then type in the number 4 or any root that you want. So we're going to make it a 4th root, and inside the root we'll type in 1/5. And we'll get 0.669.
Why can't you just flip or turn the square root or the 4th root into -4 power?
The 1/4 power. You can also do that. Okay, so take a look at this. We've discussed how you can convert a root to a power. If you have a 4th root, that's equivalent to a power of 1/4. So on your calculator, you can type in 1/5 to the 1/4 power, and you'll get the same answer. Okay, it just depends on what you're more comfortable with using. But I did just want to show you that option, how you can choose any root you want. Okay, so either way is fine. So if we write our, let's see, I'm running out of room. If we write our final equation, g of x equals a value -1, b value 0.669, power is x, and c value is 3. All right, there's our equation. All right, so this is our 4th example that we've done by hand, okay, that we can physically figure out the equation of an exponential function based off some data points, based off a graph, whatever information we have. We are going to take a look at, though, some examples that are going to be very difficult for us to figure out by hand because maybe the data points do not exactly resemble an exponential function. Okay, we're going to let the calculator do some of the work for us, but your calculator can only do so much. Okay, we have to be aware of that. Your calculator can only figure out certain types of exponential functions. Do we remember, I know it's a long time, but do we remember from the beginning of the year when we typed in a data table on the calculator and we let the calculator find the equation for us? It was something we did like within the first few weeks of school, so I understand if we don't remember. If I use the word regression, does that make a little light bulb go off? Not at all. Okay, well let's try that. Leave this page available. We're going to type it or write down some of the buttons that we're going to press, but we are going to take a look at the example on the next page at the same time. So maybe keep those 2 pages handy. All right. Like I said previously when we started this exponential unit, exponential functions are very, very common in biology or some science classes because they can model population growth or even population decay. Like if there's some type of animal going towards extinction or maybe some type of disease or bacteria that's being killed off. So we do have some real-world applications to this type of function. Okay, so take a look at the next page. A pharmacologist is testing a new antibiotic. At the beginning of the first day, there are 2,500 bacteria in a culture dish. So that's kind of your beginning amount. At the end of each day, the number of bacteria present is recorded in the table. So notice how we're starting with 2,500, but at the end of day 1, we only have about 2,100 left. Okay, so if we're using an antibiotic, it makes sense that the bacteria should be decreasing because it's killing it off. Okay, it's getting rid of that bacteria or disease. Can we, first of all, just take a look at the table or think about this scenario and whether it models exponential growth or decay? As time goes on, is the bacteria getting increasingly larger or approaching an asymptote, if we think about a graph? approaching an asymptote. Can we think about what that asymptote may be? 0. Okay, the bacteria is getting less and less and less and less. Okay, so we are approaching that extinction value of 0. So we'll say decay because as time goes on, the bacteria amount approaches 0. Okay, that horizontal asymptote value. All right, so part B, use regression capabilities. Okay, that's a vocabulary term meaning finding the equation of best fit. In algebra, you did the line of best fit, but now we're having curves of best fit to find the equation that would model this data. So from the beginning of the year, do we happen to remember what buttons we have to press in order to type in this data table in our calculator? Do some of us have maybe muscle memory from the beginning of the year? Like, where does your finger go if you want to type in a data table? Yeah? Okay. Okay, so if you hit second graph, that's definitely going to bring up a table of values. This, however, is a table of values for an equation you type in. Okay, so I already have a graph there. This is a table of values for my graph. I want to type in this specific data though. I want to type in X's and Y's. Yeah? Say it again. Stat. Okay, so hit the stat button. I like it so far. You want to keep going, Maggie? Okay, we're going to select edit. Notice how it's already selected. It's highlighted, so we're going to hit enter. Okay, we're looking for this L1 and L2 column. So depending on the calculator you're using, the numbers might already be in there because we did this last class. But you want to type in the X values in L1 and the Y values in Y2. So take a second and do that if your calculator doesn't already have those in. Maybe in the meantime, we'll write this down. So we're going to hit the stat button, then hit the enter button. Okay, to select the edit option, and we'll type in data in L1 and L2. So once your data is in the calculator, we have to tell the calculator we want it to find an exponential function for this information. Okay, we don't want a line, we don't want a parabola, we want exponential. Can we figure out where we can go from there? Maybe we need a refresher. Okay, we're going to go back. You have an idea, Maggie? Yeah. Hit stat again. Okay, hit stat again. We're going to scroll over to calc. And this is kind of a list of options as to which equation you want to use. At the beginning of the year, we did linear regression. That was number 4. We did quadratic regression. That was number 5. Maybe we did cubic regression, number 6. Not sure if we got there. Notice how there's quartic regression, if you want a power of 4, but we're looking for exponential. Can we find it? It's 0, okay, EXP for exponential. So we're going to hit the stat button again. We're going to scroll over to calc, and we're going to choose number 0, okay, at least for this section, because we've done other options in the past. All right. So we'll go ahead and hit 0. Now, depending on your operating system on your calculator, this screen may or may not show up. This is just your calculator's way of double checking to make sure that you did everything you wanted to do. So did you list your X values in L1? I'll hit enter for yes. Did you list your Y values in L2? I'm going to hit enter for yes. We are not going to care about the frequency list or storing the equation, so we're just going to hit enter for those. Basically, we're hitting enter until we hit calculate. Okay, and then you should have some numbers that pop up on your screen. We'll pick up there tomorrow.
No mistakes.
No, they're, I